problem you are going to challenge. Okay. So I guess if there's no other problems, there's no questions, maybe we can start right here. So the opponents, are you ready for your new challenge? If you do, please make your pitch. And make your pitch, please.
We would like to challenge problem number 3.
On behalf of the laboratories, we accept.
Number 3, that is. So if there is an objection, please write down the problem number, and all the groups, please write down the name of reporter, opponent, and reviewer. So the reporter will have 4 minutes, roughly, more for your preparation. You may start earlier if you like.
I would like to start.
Okay.
Okay, so good afternoon, dear doors and debaters. Today I'm going to report on problem number 3, the lapo. So this is the introduction. Okay, so first let's take a look at the problem statement. We attach a ball to each end of the string and connect the center of the string to a pivot. So when the pivot oscillates along the vertical direction, the balls will collide and then oscillate with increasing amplitude. Investigate this phenomenon. So I think the key questions here is the effect of the collision in the phenomenon and the relevance between the frequency of the pivot and the amplitude. So first, we would like to define the amplitude as the maximum angular displacement at the highest point right here. And the key units we will be using here is the radians. And this is our observation video. Okay, so as you can see here, the ball will have an increasing amplitude, and the amplitude will change over time. So to have a good understanding of the trajectory of the lato, we plot a phase space diagram. Here, we can observe that there is a stable oscillation around here, with the amplitude changing within this range. And this place is the collision phase between the two balls. And through this graph, we can calculate the highest amplitude at this point. And this is our theory. So we first assume that the motion of the pivot could be estimated as a sinusoidal wave. So we can, through this equation and differentiation, we can calculate the acceleration of the pivot. Through this, we can calculate the acceleration of the ball with the g plus the ay. And by substituting into this equation, we can and in the natural frequency, we can calculate the equation of motion as this, with no consideration of damping. So if the ball collides right here, it is inelastic collision. Well, this causes energy loss, which in turn causes damping. So if we factor in the damping of the collision, then we can calculate the whole formula as this. So if we assume that the ball is symmetry, the balls switch from each side during each collision. So if we factor in the ball size, this will be the total equation of the motion. For intuitive explanations, the frequency will get multiplied by 2 due to it being on the same side. So this is the numerical solution. As you can see, under the resonance condition, the amplitude will reach a maximum at 2 times the natural frequency. And as you can see from the phase space diagram here, the amplitude is constantly increasing at the resonance state. So to clarify the chaos right here, we use a Lyapunov exponent as our model. So for each point in the phase space, we can define the x, vx, y, vy, and z, vz. So we can find the nearest neighbor to compute the initial separation. And then we can calculate the slope via the Lyapunov exponent. So the Lyapunov exponent is calculated as this. So we have a 6-dimensional phase space with the pivot place and the velocity and the 2 balls. So it's a 6-dimensional phase space. We can observe from this graph that there is no chaos decay. Okay, so to sum up the characteristics, we have a nonlinear equation. It is deterministic and sensitive to the initial conditions. It also has an infinite lifetime. So with a Lyapunov exponent of 33.73, which is bigger than 0, we can classify this phenomenon as permanent chaos. Next, we would like to classify the phases for the lato-lato. So at the first phase, the collision will only happen downward. And at the second phase, the collision will happen at the 2 sides. So this will only happen at the resonance conditions. And yeah, we will do the first experiment, which is to calculate the damping caused by the collision. So this is the equation of motion. If we factor out the pivot oscillation in our experiment, then we can calculate the damping ratio. By substituting the math equation, we can estimate the motion of this equation as this. So if we assume that collision is the main factor causing damping, from the energy equation, we can get this exponential decay. And this is a method of calculating the coefficient of restitution. And this is our experimental setup. So this is the theoretical relation between the coefficient of restitution and the damping ratio. However, there are other factors at play. And this is the data analysis, which we use decimals to fit the damping ratio as this. So for the discussion right here, we can calculate the theoretical damping ratio through the coefficient of restitution. However, we can see that the actual damping ratio is much bigger than the theoretical damping ratio calculated by coefficient of restitution. This shows that the collision is not the whole picture of the lato-lato. So we use the calculation of the damping ratio so that it can better account for other energy losses. So now we'll do the first experiment on the pivot's frequency. So this is our experimental setup. We use a Lego machine and the lato-lato with the 2 balls with this mass. And then we have different frequencies to test. So this is our experimental videos. So as you can see here, when the frequency reaches to resonance conditions, the amplitude will get larger. And this is the results of the theta to t graphs and the angular velocity to t graphs. So as you can see right here, this remains relatively stable. And then here, you can see a beat like right here. And from this graph, you can see that the angular velocity will jump down due to the collision. And you can see that the magnitude of the theta will increase when the frequency decreases, reaching the resonance case. And this is the result of 2.42 Hertz and 2.1 Hertz. So at 2.1 Hertz, it is very, very close to the resonance, and the amplitude is bigger than 90 degrees. So at here, the conditions are pretty unstable. So we can only consider the conditions of this state right here. So we can observe that there is a stable state through the phase space. And we observe a phase space stretch, which is caused by the energy increasing when it is close to a resonance state. So as you can see right here, we can calculate the amplitude through the phase space. So this gives another explanation of chaos, as the phase space stretch is a fundamental characteristic. So we will do another phase space on the resonance case, and we can find that the phase space of the resonance case is pretty unstable, and it has a much bigger amplitude than the other cases. And we will analyze the beat, which I had mentioned earlier. So here, the pivot frequency is 3.08 and 2.67. Through the Fourier transform, we can get the frequencies. And this is the frequencies that have been calculated through the numerical solution. So from the theory, we can see that there is a pendulum frequency and a pivot frequency. However, in our experiment, we only see the pivot frequency. And the pendulum frequency is almost non-existent. And from this graph, we can also see the same story with pivot frequency and the pendulum frequency. However, the pendulum frequency the pivot frequency is only observed in the experiment, and due to the frequencies being very close, due to nonlinear systems, the beat will occur. So we have a hypothesis on why this happens. The hypothesis is the synchronization of the lato-lato. Due to the string stack, the effective length of the lato-lato will be synchronized to fit to the pivot frequency. So the equivalent L will be much smaller than the L plus R. So the resonance frequency can be modified to a larger extent to fit a stable state. This is why at larger frequencies, the synchronization may happen. And this is the verification, which we calculated through the Fourier transform, and we find that the frequency right here is equal to the pivot frequency. And we can see at the highest point here, the collision happens, and at the lowest point here, a large angle occurs. So this is the comparison between the theory and experiment. This is the amplitude, and this is the hertz. Well, in this graph, there are no error bars because we only consider the largest amplitude, which, as the power statement had mentioned. And we can see that there are the deviations right here, which is caused by string stack causing a decrease in energy. And the deviations right here are caused by the resonance, the synchronization, which is also caused by the string stack. So this is the nodule. When the amplitude increases when close to resonance frequency, and the stable state occurs due to string stack causing synchronization, and beat occurs due to nonlinear effects of motions causing Hoffman frequencies. Next is the experiment on different string lengths and the amplitude. So this is our experimental setup, which we use different string lengths, and this robust setup prevents the plane movement. And this is our hypothesis. So according to our movemental equation, for small angles, the angular acceleration will be proportional to the L at the power of -1. So when the L gets bigger, the amplitude should get smaller. And from our experimental videos right here, we can see the effect. Okay, so this is the results from the theory and the experiment. So as you can see right here, we can classify it into two cases. In this case, the biggest amplitude is smaller than 90 degrees. So you can see from the theoretical curve, we can fit a Gaussian distribution. And we can see that the experimental Gaussian distribution is a little bit bigger than the fitted theory. Well, this is due to the synchronization. And this is another graph about the 50 centimeters part. And as you can see right here, at the 40 to 50 centimeters, the amplitude is much smaller than the 20 centimeters and the 30 centimeters. And the next case is the 20 centimeters and 30 centimeters, which the theoretical relation is bigger than 90%. So as you can see right here, this shape represents a sail, and the theoretical and the experimental relation are pretty similar. And I'll explain why this happens. So this is the same story that I have just talked about before. Okay, so this is the theoretical explanation. So at the under 90 degrees, the force can be modeled with the sign, and it only has an upward trend. So this is more stable for Gaussian fit. However, when it reaches more than 90 degrees, you will have this relation, which the distributions might differ, so you cannot use a Gaussian fit. So this is the nodule. So the amplitude increases when close to the resonance frequency, and the amplitude decreases as the length increases. So when it's lower than 90 degrees, it can be modeled as Gaussian, and the experimental results have deviation due to synchronization. And the bigger than 90 degrees, the results differ less from the theory due to a lower string length. So this is the conclusion. So we can answer the key questions from our problem statement. The effect of the collision phenomenon. The collision could be considered as damping in the pendulum system, and the collision contributes to a Ball switch assuming symmetry, making the resonance frequency 2 times the natural frequency. The relevance between the frequency and the pivot and amplitude. So the ball oscillates at higher amplitudes when the pivot frequency is close to resonance frequency, and the amplitude is lower at long string lengths, and the resonance frequency is also lower with a smaller natural frequency. And this is a quick summary. And this is my reference. Thank you.
I want to ask the reporter some questions. Can you turn to take the set of page?
You mean this?
Yes. What is the exactly so you use a motor and
Yes, I use like a flywheel and there's 2 suspension points to make it vertical motion.
the loose of the string, because when
You mean the string stack or something?
because when this goes down, it will lose.
Well, yes. So I have said that the synchronization is caused by the string stack, like in this theory up here.
Okay. Why did you fit the distribution of spectrum to guys?
Well, okay. So I can show my appendix. And I also fit the Lorentzian, and I find that the Lorentzian is not as accurate as the Gaussian. And I think it is okay to fit a curve for non-linear numerical results. It's not in appendix. The Lorentzian fit is not better, so we use the Gaussian.
So what is the
Okay, so the meaning here is that we can find like the middle point of the resonance, and we can see that where is the resonance happening. Yes.
So what's the attached force function of the
You mean we use a sinusoidal equation to approximate, which I mentioned in my slide of my methodology, my theory. Sorry. So I have it.
Okay. Because the early Three minutes.
observation 的话，我们主要是讲可以了解但还有 period change。experiment 能不能增一下？然后还有问我是更高一些，那你前面的话。
Hello, I'm the opponent of numerical animation. I'm going to oppose problem number 3. First, let's look at problem 3. Attach a ball to each end of the string and connect it. And when the pivot oscillates along the vertical direction, the balls will start to collide and oscillate with increasing amplitude. So the key point is on the effect of the collision and the relative between the frequency of and then is the report overview. In the observation, they use the pendulum model and see the increasing amplitude over time. And in the theory, they use damping model and oscillation theory, and they also have the pendulum frequency and the pivot frequency, and they collide of two balls, and they use non-linear exponent thing and Gaussian distribution. And the experiment and conclusion, they use Lego model to simulate, and it gets stable state through the phase space graph. And in the chaos experiment, and they also measured, they also see the chaos experiment when in some omega, and they compared the max amplitude. So they compared the max amplitude and the string length versus amplitude, and then is their amplitude increases when close to resonance frequency. And then is their pros and cons. Their pros is that they have clear phenomenon and clear video, and they explain them with pictures well. And although it has some deviation with the theory, but they also explain it well, and they present their data as well, and it's also showing clear. But their cons is the explanation of the graph is too fast and the lack of data. And so I would like to discuss with the opponent about the period change and the calculation of the driven force, damping model of chaos, and the loose. And for the experiment, I would like to talk about the loose of the string, the driven force, and why use Gauss to fit, and the vibration of the load. I would like to invite you.
Okay, let's start. Move to the next phase.
And you?
So, reporter, please stay ready.
Can you turn to the damping model?
I mean the damping cost by equation. So I actually have two sides. Is the equation of motion or how I calculate the damping coefficient?
Okay. And how you calculate?
Or how calculate the damping coefficient?
No. The first.
Oh, the equation of motion. Yeah.
Why you use damping model too?
Well, because it is an inelastic condition and it causes like an energy dissipation in this system. So I use to model damping of the pendulum.
But so you say that because the electric the change of the force is proportional to the velocity, so you use
What change of the force?
So, but the collision is like it is not.
The collision is inelastic, so we use to fit a damping model because of energy dissipation, which I have talked about in this slide. If you use an energy equation right here, you can calculate the decay with the coefficient of dissipation.
So the damping model is used to calculate the inelastic.
Yes, inelastic collision. And also there are other factors at play causing a dissipated system. Like, for example, like you have mentioned, the string being loose will also cause some energy loss and air resistance. But this it can all be considered if we do an experiment on the damping, like with a graph, and we understand.
Calculate coefficient of the.
You mean the damping ratio?
Yes.
Or if we use an experiment and we fit up this graph to calculate it.
But when it is collide, because the damping model is like maybe ABC, like we have this and plus.
Yes, yes.
But the collision is like it goes this and this. So it's not happens all the. This is like.
Well, actually, I disagree. So what we're doing here is actually measuring the amplitude, right? So we have a theta to theta graph. So here, it is still exponential decay. Like here, if you calculate the coefficient of restitution like this, the velocity will be proportional to the square, which is basically the same as the decay, exponential decay of the gradient. So it's in the same essence. And explain that. So we fit the graph of the exponential decay, right?
Yeah.
Yeah. So what we're seeing here is that we can fit like the height right here. Yeah. So the height will actually have an exponential decrease due to the velocity. Meaning the velocity will have so it's the same as we fit a mathematical equation like this. Well, there are some problems, right? The mathematical equation use the theta as the approximation, but I don't think that is a very big problem since the damping we have no other better methods to measure that.
So you think it fits?
Well, I fits.
So why you say that if V is proportional to E squared, and we get like this?
Because after like the n times, like for example, you have like so in our experiment we don't give it a pivot, we don't give it this, right? So we only have the collisions, right? So that we're gonna have an h n plus 1 and the h n. Then we will like have a relation to the power. So it is the same as this.
And why?
Because I'm sorry, because the coefficient of restitution will have like this relation. Well, actually it's 2 times because it's in the symmetry. Well, I'm actually talking about the sort of like this. You're aware of the translation. So if this can be we can substitute this table. So then the maximum the amplitude, which the height can be changed to the theta, right? So it will still be of a power.
So you said that it should be.
Oh, sorry, yes, I say that this is the amplitude.
And can you turn to? So how do you have? Did you calculate? You said that you measured the coefficient of
Coefficient of restitution. We calculate using a method like we insert velocity and we calculate it's the same
So
law.
you use this by experiment.
Yes, the experiment. So this is an experimental coefficient of restitution, and this is the experiment that we find that a constant collision is not the whole picture.
Can you calculate the coefficient from
No. Oh, you mean if we have the damping ratio and we can calculate it back?
Yeah.
Okay, so it will yes, it will be like this relation. So if you like have the coefficient of damping ratio like right here, I can know what coefficient of restitution is. However, we find that it is not very close, and so this means that the lato-lato system have other factors of energy dissipation.
Okay. I want to talk about. Can you turn to the driven force? How you calculate?
You mean this? The theory or the experiment?
How you? I think I want to ask. Can you? You said that the string is loose, and how you solve it?
Well, so in my theoretical equations, I have assumed that it is a rigid body. But however, from the experiment, I can see that from a theory, we should have a pendulum frequency, a pendulum frequency and a pivot frequency. Yes. However, we have observed that here in the experiment, only the pivot frequency exists. So I assume that there will be synchronization happening, meaning that the G right here will be the LE right here will be synchronized to the G to make it the same frequency as the oscillation.
So you said that you have a way to calculate LE and
yes, you will. Yes, you will have the. You mean the new frequency here will be the same as the omega.
So, but the tension is like this way, and if you use this, and tension is this way.
No, this is calculated through the. This hypothesis is derived through the experimental results, which I think that.
So the LE is calculated by.
We can have an LE. For example, if I give the pivot frequency of omega p, then the omega p can be substituted into this to calculate the effective L. Yes. Because in the experimental results, we cannot see a pendulum frequency.
And why did you use the spectrum to? Why do you use the Gauss to fit the distribution of the spectrum?
Well, because this is a non-linear equation, and I need to fit something that is close to the numerical terms. So I have chose two kinds of. I actually fit many things, including other types like the Stokes equation or other things. But the Gauss fits them both, so I use the Gauss instead of the Lorentzian for other types of things.
So why you fit?
Because I want to quantify the place where it happens to have the resonance. The resonance frequency, which we have confirmed that it is 2 times that frequency.
Why don't you just plug the?
Oh well, because this is a numerical solution.
And can you turn to the omega to theta graph?
You mean the phase space?
Yes.
You want the picture with the stable phase space or the unstable?
Stable.
This is the stable phase space.
So, can you? Why is there not like this?
What do you mean?
Why is the line not?
Oh, in the zero part, right here.
Yeah.
Well, this is because the ball has a size, so the smallest cannot be like in the zero.
So did you?
So for the same ball size, so as you can see in the graph, the place right here is the same in in all of the 4 phase spaces. Well, this is because we control the size of the ball in the experiment.
Did you calculate it like?
Yes, this is the arc sign of the ball and the length of the string.
Okay.
Okay, the opponent will have 1 minute.
Okay. Now it is the summary. I want to summary the discussion. The first is that the opponent. We talk about the damping model, and the opponent says that they use damping model because they are in elastic coefficient and also losing string, so they use it to calculate it. And I think if they have a way to calculate it theoretically, to calculate the coefficient theoretically, it will be more better. But I think it is good enough. And and then they miss and they assume that the string is a rigid body of the theory, but after experiment they discover the phenomenon.
Okay, I guess we have to move on. So the reviewer please stand up, and the opponent and the reporter please stand for question.
So right now I have some questions for the reporter and the opponent. So first is for the opponent. So do you think that this the whole system is a 2D motion?
I think it is near to
Near. How about the reporter?
Well, we have done measurements to find out that it is actually a 2D motion.
Okay. And so for the opponent, so you mentioned there's a stack of strings. And do you, so what like specific time interval do you think the stack of strings will happen when the lato oscillate downward?
I think when it oscillates down, it will all the time when it is
Like, is there a specific like data, like what the theta angle or something like that? Okay, and how about the reporter?
Well, this will depend on the acceleration, which I have calculated through this formula. So when the acceleration is downward, you will happen to have the string stack.
Okay, and so this question for both of you. What do you guys think? Why would the amplitude of the lato increase?
I think it's because the
Driven force. Okay, how about the reporter?
Well, the driven force is the same in a different experiment. However, if we change the frequency of the force change, then we will have, so the lato will have an increased amplitude at the resonance when the frequency of the force is at resonance.
And this one is for the reporter. So do you think that an elastic collision will result in a damping?
Well, yes.
Okay. And so, so this question is for the opponent. So you mentioned about the stack of string, and I also want to know: do you think that there's like vibration of the strings or like the rotation of the bows before the collision?
I think it will have the vibration of the string, but I think the rotation of the ball is not very big.
Okay. How about the reporter?
Well, of course, there might be some deviations. However, it is all considered in damping as the energy loss.
And another question for the reporter is that so you mentioned the lato will enter a chaotic system, and is there like any specific definition for chaos?
Well, the definition of chaos is this, which they are deterministic, and it has a positive diagonal exponent with sensitivity to initial conditions.
So you also mentioned that there's some initial condition when the lato enters a chaotic chaos. Can you like elaborate on that?
Well, I don't identify a motion where the lato is not chaos. In all my experiments, the lato exhibits the chaos and exhibits permanent things.
I think there's a specific page that you talked about.
No, that is stable and unstable, but they are all chaos. That is different.
So this question for the opponent. So time's up.
Okay, yeah. So the reviewer will have 2 minutes for preparation.
下去。
Go on, go on.
Good morning, honorable judges, fellow contestants, and esteemed guests. I'm the reviewer from Team Go, and right now I'm going to review problem number 3, Lato. And here's the problem statement, and there's a focus of the reporter. And the ball will collide at the highest point and separate at the lowest point. And here's the theory and the experiment that the reporter used. And here's some pros and cons for a reporter. So I think the reporter has a very clear demonstration of the phenomenon by showing the simulation video as well as the machine that they use to conduct this experiment. And and also have complete understanding of the theory. But there's still some cons, such as they could explain more on the experiment setup, and maybe the experiment should prove the upper half of the Lato phenomenon as well. Next. And here's pros and cons for the opponent. So they ask easy to understand question. Their question and their formats are easy to follow. And however, there's still some cons, such as they give few ask few contributing suggestion and some superficial question. So here's some discussion that discussed. So for when the opponent asks the reporter why use a Gaussian fit, the reporter responds with Gaussian fit is better to get a resonance frequency. However, our opinion is that so we agree with the reporter, but we also suggest the inclusion of the explanation of Gaussian fit and why it is better. And next, the opponent asks why use damping in the equation and how do you calculate the damping ratio. And Lato velocity is not proportional, so should not use damping in the experiment. And the reporter responds with because this is an inelastic collision, so there is a change. And there are other factors causing the dissipation. Our opinion is that we agree with the reporter because if we look at gradual decrease of the amplitude, and in the damping experiment, all resistance is already considered except slack. Next. And next, opponent asks if the string is loose, how to solve this the energy loss. And the reporter's response with in the theory, they assure it has a rigid body, and in real world we know the string will be loose. And according to a hypothesis, the length can be rewritten in different matters, and we agree with the reporter. And the opponent asks the reporter, "Did you calculate multiple parameters?" And the opponent then asks, "Why doesn't the ball go to radius equals 0?" And the reporter says because the ball has radius, and we agree with the reporter. And here's some question I have asked them. So first I say, do you consider it as a 2D or 3D motion? The reporter says yes, it's a 2D motion, and the opponent say it's a 2D motion, but nearly a 2D motion. So our opinion is that they could add a camera in the y-axis, which is like parallel, like right here, and to prove the 2D motion, since 2D or 3D affect a lot. Next, the reporter asks them how will slack effect work and if there's a specific period, and the reporter says when the acceleration is downward, and the opponent says there's no specific period. And we think the energy in the system will be affected by that. And why will the amplitude increase? The reporter says if you change the frequency of pivot with the same input force, the amplitude will increase. And the opponent says there's a driven force, and we agree with the reporter. And next, I will ask them about the vibration of the string and the rotation of the ball. The reporter said, it's all considered in the damping. The opponent said yes, but only for the vibration of the string. And we agree with the reporter. Next, I asked them about the definition of the initial condition in the chaotic system. The reporter says everything is chaos except for stable and unstable, but failed to explain further on. Next. So here's some missing point. We believe that you can prove that a 3D motion will be better for this whole experiment. A 2D motion, sorry.
Okay. Okay, now the reporter will make your final conclusion.
Okay, so for the concluding remarks, I would like to talk about the brief discussing points with the the opponent. So the opponent had asked me about how we calculated the damping ratio and if it is correct in the essence of the collision. And I think that our calculations will be correct if we consider the inelastic collision causing the energy loss. And we use the fitting of the damping the fitting of the motion to calculate the damping ratio. And they have also asked about how we calculate the coefficient of restitution, and we answered that we calculate the coefficient of restitution by doing experiments on the different velocities of collision. And they suggested us that we can make a theory about the coefficient of restitution, which I think is pretty weird since the ball's materials are not really suitable for us to derive a theory like that. And also we have discussed about the chaos with the reviewer, which they seem to understand more than the opponent. And I would like to clarify here that our chaos is the whole phenomenon is chaos, and the chaos can be separated into two kinds of phase space, with stable phase space and unstable phase space. And the unstable phase space will happen when the frequency of the oscillation of the pivot is very close to the natural frequency. And then I would like to talk about how the opponent thinks that the driving force is the main cause of the increasing amplitude. However, I think that it is not the driving force, rather the frequency of the driving force motion. And the frequency of the driving force motion will increase the amplitude at synchronization. That is because the energy is the most conserved in that case. So you have a stretch in phase space that stretches the phase space out and make the phenomenon have an increasing amplitude. And that will be my concluding remarks. Thank you.
Okay. So now the time goes to the jurors. Any question you like to ask? Okay, the Professor Han.
You mentioned that this is a static system. And how do you distinguish the stable and unstable case by reading the diagonal exponent?
I did not use the Konopnik exponent to classify the stable and unstable case. I used the phase space bracket. And as you can see right here, it is very stable around this with this diagram. And for a resonance case, right here, this is very noisy. So I think that this is unstable.
Then why did you use the diagonal exponent?
Well, we use the diagonal exponent to classify the whole phenomenon as chaos. Well, yes, there might be some different magnitudes of chaos, meaning that.
Could you turn to that page?
You mean the calculation of the model or the results? The model
Yes.
is this model.
Use this model to try to distinguish is that a chaotic system or not.
Yes.
So you cannot distinguish is that a stable or unstable system.
Yes, I use the phase space.
Okay, the second question will be, if it is a real chaotic system, then it's supposed to be very sensitive to the inertial condition.
Yes, so it's very sensitive to like the frequency.
To prove that?
Well, I think that it just can be proved through the phase space by calculating the Konopnik exponent.
No, but you did an experiment to prove that.
Oh, you mean that? But this is calculated through the phase space of the experiment.
This is a calculation.
This is a calculation from the phase space. Like there is like different points of the six-dimensional phase space, and it calculates like the deviations throughout the time. So this is the sensitivity to the initial conditions that you are asking.
Did you do the experiment?
Yes, this is from the experimental results, and it is computed through Python.
I think it's not.
It is calculated through Python code by calculating a six-dimensional phase space and getting the distance between the trajectory of the phase space throughout the time, and we can calculate the slope of it so that we know the difference throughout the time frame, which is cited from this book of nonlinear dynamics at page 99.
Okay, I guess we can, any other questions of the paper?
Maybe I want to clarify something. So I just heard reporters say something like the energy conserved most. So I would like to ask all of you, in this system is energy conserved. is energy conservation in this system for all of the reporters?
Oh, no, I have said that this is a dissipated system. However, at the resonance case, the energy will be most conserved, so it will have the largest amplitude.
I think it is not.
I also think that it's not conserved since there's an impulse energy.
Okay. So, any other question from our other jurors, or maybe some follow-up? Okay. Well, maybe Professor Bao. Okay, not this time. Okay, so if there's no more questions, unless Professor is not satisfied, we still have 1 minute or not.
I mean, did you change the condition of, for example, the position of the two balls?
But if it is a trajectory, then you will have different positions of the balls in the phase space.
I don't say it's the phase space.
The trajectory
The trajectory.
So what you're meaning is that if I can do more like a factor rotation diagram, is that what you want? Okay, so yes, we can do more experiments on like a factor rotation diagram, like with different initial conditions that is certain. But however, I think that the dipole exponent can also be calculated through the trajectory of the
I guess time's up and really up. So now we move to a grading session, please. So I guess we are all ready. Okay. So let me show mine. So please show the scoreboard. Here what I would say 8, 8, 6, 7, 8. Okay. Now we move to the opponent. Okay. 7, 5, 6, 5, and 7. Okay, that's one is for the viewer. Okay, 8, 6, 6, 6, and 7. Okay, any final comments from the jurors? Okay, if there's no further question, then we conclude our game today. Thank you all very much.
做得很好。